Hello, my name is Paul Thomas Edward Cusick. I'm a civil engineer by education, and I do research in just about every field that universities teach in. An interesting paper I have here that I wanted to present is called Ductility, Stress and Strain Theory from the Mechanics of Materials. And it's a very brief paper. There's only 13 slides. So let's get started. So Van Vleck, who's a famous author of a textbook on material science, claims that there is no mathematical relationship between the two measures of ductility, elongation and reduction of area of the specimen. In this paper, we prove that there is a relationship between the two measures that involve the golden mean parabola. Even a subject as old as mechanics, we can still make discoveries. So ductility is a measure of a metal's ability to withstand tensile stress, which is a force pulling the two ends of an object away from each other, with tension. Ductility is the measure of a metal's ability to withstand tensile stress, which is a force pulling the two ends of an object away from each other. That comes from the infamous Wikipedia. There are two methods to measure ductility. One is elongation, which is strain, delta L over L, the change in length over the original length. The second is the reduction of area, dA by dt. Van Vleck states that there is no mathematical relationship between the two measures of ductility. In this paper, we will unite the two mathematically. So now we'll have to do some math. Assume a specimen that is circular in cross section. So the area, of course, is equal to pi r squared. And if we take the derivative of the area with respect to strain, we have the circumference, which is 2 pi r. The derivative of pi r squared is, to bring the 2 down, 2 pi r, and that's circumference. So r is equal to 2. If you're familiar with astrotheology, another paper I've produced, many papers on astrotheology, some of these figures will, you'll remember them from astrotheology. So r is equal to 2, the radius is equal to 2. So dA by the strain is equal to 2 pi r, which is equal to 2 pi times the radius 2, which is equal to 4 pi. And since the area is getting smaller, it's a negative 4 pi, which is equal to minus 1.25. And 1.25 is the minimum energy in the golden mean parabola. So we visualize a parabola plotted. We have at the minimum the time on the x-axis equal to a half. If we plug the half into the golden mean parabola, x squared minus x minus 1 equals e. Then a half squared minus a half minus 1 is equal to minus 1.25. So there we have t squared minus t minus 1 equals the potential energy. T is a half, which is equal to 1 over r. R is equal to 1 over t, because E is equal to 1 over t, equals 1.25. So now we integrate the time with respect to time, and we integrate the radius with respect to time. And we end up with t squared over 2 is equal to r squared over 2, which is equal to 2 squared over 2, which is equal to 2. So t is also equal to 2, which is equal to r. So if we plug that 2 into the golden mean problem, we have 2 squared minus 2 minus 1 equals 1, which is the potential energy. Potential energy is simply mass, and kinetic energy is simply time. So a derivative that's very important in astrotheology theory, and important here too, is the rate of change of mass with respect to time. So dm by dt is equal to 2 is equal to t is equal to r. R and time, the radius and the time are equal at 2, and they're equal to dm by dt. It's interesting that m is equal to, in astrotheology, is equal to 0.01234567 and so we're jumping from 1 by 1 for each digit up until we reach 7, and then we skip 2 to 9, skip over 8, and 1 over 81 is equal to the 0.01234567. So now our Newton's famous equation F equals ma, if we take the derivative of the force with respect to time to get the derivative of mass with respect to time times the area, times the acceleration, and the position is equal to the velocity is equal to the acceleration. So the derivative of these variables is always 1 over root 2. I won't go into why, but it comes out of astrotheology. It's enough to know that the velocity and acceleration is 1 over root 2. So 2 times 1 over root 2 is equal to root 2, which is equal to the sine of 45 degrees plus the cosine of 45 degrees. So there we have 1 over root 2 plus 1 over root 2 equals 2 over root 2, which is equal to root 2. That's the energy. That's the maximum energy you can get out of a two-pole problem, is root 2, because you're adding the two poles as time is 0, or x is 0, is when cosine is 1 and sine is 0. It's the two pole. And then they meet at 45 degrees, or pi by 4. So now we use Young's modulus here. The stress is equal to Young's modulus times the strain. And so the stress is force over area is equal to Young's modulus times the strain. And the force times 1 over A is equal to Y times the strain. Y would be the energy. In this case, it's Young's modulus. dF by dt times d strain by dA is equal to Y d strain by dt. So if we take the rate of change of the force, we have a constant times 1 over 4 pi, which is equal to another constant q times the strain. So C times T is equal to QE. C over Q, to bring the two constants to one side, is equal to strain over time. And the derivative of strain of a constant is 0, is equal to d strain by dt. So the rate of change of strain with respect to time is 0. Then the rate of change of the force with respect to time times the rate of change of strain with respect to area is equal to Young's modulus times the rate of change of strain with respect to time. So dF by dt times 1 over, there's that 4 pi again, is equal to y times 0. So dF by dt is equal to 0, and t is equal to 0. Time is 0. But we know that dF by dt is equal to root 2 at t equals 0. T squared minus t minus 1 equals potential energy. So 0 squared minus 0 minus 1 equals potential energy. Potential energy is equal to minus 1. The potential energy equals mc squared. M is equal to minus 1 over c squared. And it's equal to 1 over 9. 0.111. Now the kinetic energy is equal to time, or time is just simply kinetic energy, is equal to 1/2 mv squared, standard equation from basic physics, which is equal to 0. The time is 0, the kinetic energy is 0. So 1/2 minus 1 over c squared times v squared equals 0, minus 0.555 v squared minus 1 over 18 v squared equals 0. So 1 over 555 is 1 over 180, or 1 over 18. It's 1 over pi. And I mean, v turns out to be 0. Continuing along with Cloak's law there, we have sigma equals Young's modulus times the strain. The force over the area is equal to the Young's modulus times the strain. dF by dt divided by dA by d strain is equal to dE by dt. So we know root 2 is dF by dt times, we know that dA by d strain is equal to 4 pi equals y times the rate of change of length with respect to the original length. So that's root 2 times 4 pi is 1.777, which is equal to the work, which we also know from astrotheology, is equal to Young's modulus, which we know is actually 0.4233, which is pi minus e. I called it Q's in a very humbly in a previous paper, and that's multiplied by the d strain by dt. So d strain by dt is equal to 1.77 divided by 0.4233, which is equal to 42%. And that has no units. So this is slide 10 of 13, I think there are. We have sigma equals Young's modulus times the strain again. So we have force over area equals y times, we know the strain now is 42% or 0.42. F divided by dA by d strain is equal to y times 0.42. We know the force is the super force is 8/3, which is equal to 2.666 divided by A times delta A, which is equal to y times 0.42. So 2.666 divided by, I'm sorry, that's not A times dA, it's small, it's a subtract, so it's A minus 4 pi is equal to 0.4233 times 0.42, and area minus 4 pi is equal to 2.666, the super force, divided by Young's modulus, 0.4233, which is multiplied by 0.42, which is equal to 15. So area is equal to 15 minus 4 pi, the amount that it shrunk by, which is equal to 2.427. So 2.666, the super force, divided by that 2.427 is equal to 0.4233 times the strain. And we have the strain comes out to be 2.5956, which is approximately equal to 0.26, which we know from astrotheology is Poisson's ratio for the universe. So finally, if we take that 0.42 and divide it by the 2.6 or 2.5956 equals 1.618, which is the positive root of the golden mean for Hubble. So in conclusion, after this brief talk, We have provided a mathematical relationship between the two measures of ductility. And the reference there is Van Vlak's textbook, Elements of Material Science and Engineering by Addison Wesley, which I took way back in 1989 and I'm just using now. That's my 15 minutes on ductility, stress and strain theory.